Hi everyone, my name is Jonathan and I'm going to be presenting a paper on behalf of myself and Josiah from the University of Cape Town. The paper is about deep learning traffic classification in resource-constrained community networks. The presentation is going to start with an introduction on the background to the project as well as the project aims, and then a brief overview of related work. Then we're going to dive into the methodology and finally take a look at the results and conclusions. Firstly, in background, community networks. Community networks are a solution to providing internet access in rural areas around the globe. They're typically formed by a small group of people coming together to develop a network infrastructure in their local community and then creating some sort of access point to connect the network to the wider internet. One of the kind of pain points experienced by these community networks are slower internet speeds than their urban counterparts. Something that they can do to kind of make this slow internet speed less of a problem is invest in QoS engineering, which is used to manage network traffic with the goal of reducing latency, packet loss, and jitter. This can be done by prioritizing traffic from some applications over others according to predefined network rules. For example, we might want video traffic to, from a video call, to be sent through a lot faster than, say, an email. And this can be done by using online network traffic classification tools, such as the machine learning ones implemented in this paper. It doesn't strictly have to be machine learning, but we're focusing on machine learning. So, this project aims to analyze and compare the performance of 1D CNN, MLP, and SVM machine learning models for this real-time traffic classification task using packet-based classification in a resource-constrained environment. The project has the following aims. Firstly, to investigate the trade-off between speed and accuracy for each of the models listed above. So we don't only want to see how accurate we can get our models to be, but we want to make sure that they can classify fast enough to be practical in a community network context. Secondly, we investigate the trade-off between payload length given to the model and model accuracy. So we want to see if we can trim the packet payload to a smaller subsection of the data and get a similar accuracy with a faster classification speed, since the models can be smaller. And then finally, we provide some sort of basis and methodology for recommending a model to a community network based on their CPU constraints. So related work, not many studies have been done for packet-based classification, and those that do have not considered the resource constraint problem. There was one relevant paper for the 1D CNN task where they classified individual packets and managed to achieve an F1 score of 98%. However, no information was provided about the classification rate, so we don't know if this model would have been practical in a community network or low resource environment context. And then finally, there is no relevant related work for packet-based classification for MLP models. The data set, this was collected from the Ineti Ocean View Community Network in South Africa, and it comes in the form of PCAP files, which were stored in a data repository at UCT. Pre-processing. So we took these raw PCAP files and split them into individual flows. We then labeled each flow with a deep packet inspection tool called NDPI. We then extracted the IP payload from each of these packets. Thereafter, we selected and sampled balanced classes before separating them into train, validation, and test sets for our models. Experiment design. So after the pre-processing stage was completed, the following steps were followed to execute the experiment. First, we varied the input length. So for each packet, we split it up into either the full payload and the label, or 3/4 of the payload in the label, or half the payload in the label, or 1/4 of the payload in the label, to train our models on different packet payload lengths. Secondly, we established a baseline with the SVM model. So this is the simplest kind of basic machine learning model that we use just to see how accurate and fast that one would be. Then we looked at our deep learning models, so the 1D CNN and the MLP, and we selected a set of hyperparameters, and we used a grid search technique to look at those different hyperparameters and see in training our models. We then did performance evaluation, so we took each of those models, looked at what accuracy they could get on the test set, and the prediction rate that they could get, so how fast could they, how many packets could they predict per second. And then finally we looked at some sample hardware constraints that we might expect to see on a community network, and looked at what the best model is that we could use for that network. So model accuracy comparison, here we see for the different input lengths what the highest accuracy we could get for each of our models. Typically the 1D CNN performed best, followed by the MLP, followed by the SVM. And input length, the full input length seemed to perform best across all models, but this doesn't yet say anything about classification rate. So this figure here is for the MLP, and it shows each dot is one of the models trained in the grid search that we performed. And what we see here is a negative relationship, kind of weak negative relationship between test accuracy and prediction rate. So the faster our model got, the worse the accuracy was. Cool. Then similar thing for the 1D CNN. We see that the really fast 1D CNN models also didn't have that great an accuracy, and it's only once when we looked for a model with a higher accuracy, the prediction rate was a lot slower. So next we come to the community network model allocations. So the actual methodology for picking these kind of network constraints is explained a bit more in the paper, but for now all that's relevant is that we've got 6 different community networks that we considered, from kind of lowest resource environment to highest resource environment. And what we see is that only in the lowest resource environment would we pick the SVM with an accuracy of 64%. And then in a slightly higher resource environment, we picked an MLP with a 365 byte input payload. So this is an example of a smaller section of the packet data being used to get a faster model with a lower accuracy trade-off. And then in the kind of moderate resource environment, we still have MLP, and only in a really fast community network do we allocate the CNN. But interestingly, this still isn't the best CNN model that we got across all the training, but it's the only one that would work for this environment. So yeah, to work out which model should be allocated to which network environment, we picked a minimum rate, so packet classification rate that was acceptable, and then we picked the best model that would meet that packet rate classification for the given CPU constraint. In conclusion, we find that the 1D CNN attains the highest accuracy, but that the MLP can perform much faster without sacrificing significantly on accuracy. Secondly, there's a general inverse relationship between prediction rate and test accuracy. So we, in lower resource environments, we do have to sacrifice on accuracy if we want our traffic classification tool to be fast enough for online classification. And thirdly, full payloads achieve higher accuracy at the cost of performance. So as we saw earlier, we can get a faster model in exchange for using more of the packet payload. We can get a faster model in exchange for dropping some of the packet payload, but we sacrifice accuracy. And then lastly, the MLP is generally best for the community networks that we considered, However, the 1D CNN is better if the community network has really advanced hardware, and only in like a really low resource environment would be considered the SVM. Thank you.